I'm Dr. Foster. I'm substituting today for Dr. Chang. This is Chemistry 108. It's May 7th, 2015. I will be continuing with just the end of Chapter 9 and starting the beginning of Chapter 10. We're going to start with the carbonate anion, CO3 2-. So first, we're just going to draw the Lewis structure, then assign formal charges to all of the atoms. So first of all, CO3 2-. What's the general structure going to be? So if you have a C with O3, then you're going to have C in the center, right? C in the middle. And then the O's, the oxygens, are going to be around it, OK? So now when I'm doing a Lewis structure, and I'm just going to tell you right now, different people sometimes approach it a different way. So this is what I do, is I set it up first, right? I know that this is going to be the central atom. There's one of them. We mostly do symmetric things in Chem 108, and then I put the oxygens around it. I need to know how many total valence electrons I have. So carbon is 4. So total valence, carbon is 4. Oxygen is 6, but we have 3 of them, so that's 18. So far the total would be 22, except that you have 2 extra electrons, right? That's what this means right here. So your total is actually 24. So to be a valid Lewis structure, you have to include 24, no more, no less electrons. OK. So I always say the 2 big rules of dot structures are, number 1, use the correct number of valence electrons. Number 2, whoever needs an octet needs to get an octet. OK? So carbon and oxygen definitely need octets. OK, so I've already used some electrons just to connect this thing together. So I've used 2, 4, 6, right? So I'm going to start filling in octets and see what happens. So I have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Now you notice, again, the way I do it is I always go from the outside, the outer atoms first. OK, now what's wrong with this picture? Carbon does not have the octet, but I've used 24 already. So a double bond is going to be better. So that's not going to work. I'm going to make, basically, I'm thinking of these as going into a double bond. So this oxygen is going to share those 2 electrons with the carbon. That way they both get the octet. I've used 24. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Because this is an ion, I put it all in brackets with a -2 on the outside, right? OK. Formal charges. So how do you calculate formal charge on each atom? How do you calculate formal charge? Yes?
Formal charge is the number.
Go ahead, go ahead.
The number of valence electrons, the number of bonding pairs, minus half the number of bonding pairs.
Yes. Do you want to?
The way I learned it, I think it's valence electrons minus how many the bonded electrons, and then how many are unbonded.
OK, the half is important, though, right? So it's half the bonding, and the non-bonding, sometimes known as lone pairs. OK, so let's look at carbon. Valence electrons in carbon? 4. OK, that's just off the periodic table without even looking at this. Now, carbon has no lone pairs, no non-bonding electrons. It has 4 bonds around it, right? A total of 8 electrons. Half of those 8 electrons get assigned to carbon. Okay? So this would be 4 minus 4. That's half of 8. Half of the bonding electrons gives you 4. Another way to think of it is just count the bonds, right? Carbon has 1, 2, 3, 4 bonds. So half of the bonding electrons is actually the same thing as number of bonds. Okay, so carbon, 4 minus 4, has a formal charge of 0 in this structure.
So valence electrons minus half of the bonding plus
The non-bonding, yeah. There were no non-bonding on there, so we didn't have that. But we will for the oxygen. Okay, now there's actually 2 types of oxygens. There's 3 individual oxygens. But if you look at this one right here and this one right here, they're in the same situation, right? They both have a single bond and then lone pair, lone pair, lone pair. Okay, so let's look at this type of oxygen. So oxygen has 6 valence electrons, right? Okay, how many bonding electrons are right here? 2. Half of those get subtracted. Okay, so minus 1. How many non-bonding electrons are there? Count them all. 6, right. So you notice I have this in parentheses here because I'm adding up here. This is how much oxygen kind of started life with, right? The valence electrons, that's an oxygen atom by itself. This is describing its situation in this molecule. It's got 1 from half of the bond and then 6 as lone pair. So this is 6 minus 7, which equals -1. So both this oxygen and this oxygen would be assigned a formal charge of -1. The carbon we already figured out was 0. So we do need to do this oxygen separately because it's in a different, it's got a different situation there. So we have oxygen. Again, we're going to start with 6, the valence electrons. And then we're going to subtract. So how many bonding electrons do we have here? A total of 4. Half of those are assigned to oxygen. So that's 2. Then the non-bonding electrons, a total of 4. Those are entirely on that oxygen. So now this is 6 minus 6. So that oxygen has a formal charge of 0. Okay. Now, this is a molecule that does have resonance as well. So okay, so what did you learn? You said you touched on resonance structures. You didn't?
We didn't lab.
because of the definition, but that's it.
Okay, so their definition. Just tell me that then. Nobody. Oh, you did in lab, not in lecture. Okay. You did? Okay, so what do you know about resonance structures?
Well, we learned is that if it's a double bond, you will move it around.
Okay, so if you have a double bond, that's a good way to recognize that you might have resonance structures. So essentially, these are different Lewis structures. Okay, so resonance structures are different Lewis structures for the same molecule. And these are used when one Lewis structure does not accurately represent the true structure of the molecule. So what does that mean? For example, you can tell experimentally that all the carbon to oxygen bond lengths in carbonate are actually the same length. That doesn't make sense from the structure that we have here. Why does that not make sense to say all the CO bond lengths are the same length? Because double bonds are shorter than single bonds. So that structure can't be giving us the whole picture, because that structure says one bond should be short and two others should be a little bit longer. So what happens is, I'm going to rewrite this one. Now, when I was doing this dot structure, counting up my valence electrons and working out the octets, I just decided to put the double bond here. There's no reason I couldn't have put it on this oxygen instead, or on this oxygen instead. So when you're drawing resonance structures, you're basically showing all of those possibilities. So the second one for this the second resonance structure would have a double bond somewhere else. Yes?
I have a question. Why does it matter whatever way you shape it? So if I drew a Lewis diagram of, let's say, the structure, right, does it matter about the order of which I put in?
Are you saying does it matter where you put the double bond? Okay. In a question like this, to the best possible answer would be to draw all three resonance structures. So there's some where there aren't any choices. Let's say CH4. There's no double bonds. There's no choices. It's just C bonded to 4 H's. If there's a double bond, then you show the possibilities exactly like we're doing here. Now, if you're saying, is this dot structure good enough? Sure, it's one, but it's more accurate to put all the possibilities and say that they're resonance structures of each other.
Does it hold true for triple bonds too, or no?
Yes, it can go with triple bonds too. With triple bonds, there's sometimes more than one possibility as well, yeah. Are there any exceptions where there's triple bonds and no choice? Yes, there are. So let me finish this one and then I'll. So there's one more possibility for this. So this is C double bond O. So now the double bond is over here. So in these different resonance structures, the formal charge of, let's say, this specific oxygen atom could be different. Like we found this one, that is the one that was 2 + 4. So this one was a formal charge of 0. In this one, the right-hand oxygen has a formal charge of -1. So the formal charges on the specific oxygen changes, but they're all resonance structures. Okay? So what this means is, what this truly means is one Lewis structure does not really tell you the full story. It does not mean that the molecule is somehow flitting around and changing from one mode to the other. It just means that Lewis structures, even though they're very useful and they help us predict some things, there's not really a good way to draw one structure to represent carbonate that shows that all the carbon-oxygen bonds have the same length. So. Now, you were asking about triple bonds. An example of something with a triple bond. There's a molecule that has a triple bond. There's nowhere else you can put this bond because hydrogen. What do you know about hydrogen in dot structures? It only gets 2 electrons, so you don't really have options as far as where to move those bonds around. Okay.
How can we identify that it's a resonance?
if a molecule has resonance structures, you mean? Looking for double bonds is a good way to think of it. Yeah.
We have to be given the like thing that says all the CO bond links are equal.
No, actually, just by drawing this, when you see that, well, you're making a choice. I see that I need one double bond. Where am I going to put it? If you kind of arbitrarily, I'm going to take this one, well, then you could take the other one as well and call it, and those would be the resonance structures.
Okay, can you give an example where a triple bond would work?
Okay, so carbon dioxide. Did you guys do this one? This is a very, okay. It's a very popular example. So carbon dioxide. How many valence electrons? You're thinking of the mass. Carbon is 4. 16, okay? Carbon's going to go in the middle. 2 oxygens on either side. They have to be connected just to be a molecule, so I'm going to use 4 electrons just to connect it.
Isn't it carbon 12? So it would be equal. 6 and 6 and then plus 4. Or 16, 12.
I think you're thinking of mass too or something. Right, 16. Okay, so now we're going to fill in those electrons, keeping the octet rule in mind. So I've used 4, right? 2, 4, 6, 8, 10. Now from here, 12, 14, 16. Okay? This doesn't work, right? Because carbon is short. Carbon needs an octet. So now here, there's a couple of possibilities. One is you could say, okay, I'm going to make this go into there and make a double bond. How many electrons would carbon have if I did that? 2, 4, 6. That's still not enough, so I'm going to have to do something else. Now, your second option, you could actually do this. Make a triple bond. Yes, you could make 2 double bonds. So there's options, okay?
If you make 2 double bonds, is there resonance or not?
No, well, the triple bond would be technically a resonance structure. Now, let's just look at both of those. Okay, here is an illustration of what formal charges are used for. Okay, so in this top one, what's the formal charge on the carbon? 0, because it has 4 valence electrons minus half of these 8 bonding electrons is 4, so that's 0. Okay, in this one, the oxygens are both in the same environment, right? They're both double bond with 2 lone pairs. So what's the formal charge on this? Well, I have 6 valence minus half of the bonding electrons. 4 bonding electrons, half of that is 2. The total number of non-bonding electrons. So 6 minus 2 plus 4 is 0, right? Okay. In this one, what's the formal charge on carbon? It's also 0. 4. Carbon still has 4 bonds, so that's that. Okay, now these oxygens are in different environments. So this one, I'm going to do this one right underneath. So I have 6 valence electrons. I'm going to subtract 1, which is half of the bonding electrons. I combine that with the non-bonding electrons, that's 6. And I get -1, right? This one is different. This one is 6 minus 3 for the bonding, and 2 is plus 1. Okay, here's what formal charge is used for. If you're looking at two options like this and you want to know which one is better, the Lewis structure with lower values for formal charge is better. Okay, so this one is 0, 0, 0. Smaller formal charge, that's a better, more valid Lewis structure. Okay, so out of these two, you would say, well, this one is actually just a better structure. This one, you could do a resonance structure of this, right? Because you could put the triple bond here and the single bond there. But these are considered not as good as this one because they have formal charges. Okay. So, structure with lower formal charges is better. If you have no choice, such as we had with carbonate, we didn't have all zeros. There wasn't an option that had all zeros for formal charge. If there are non-zero formal charges in your Lewis structure, a structure that has the negative charge on a more electronegative atom is better. So, questions on that? Okay. Now, you guys are going to have some more practice with this later, so I want to go on to the next topic, which is about deciding what the geometry of a molecule is. So if there isn't like a specific question on this, I'm just going to go on to that. Sorry? Yes, yeah. So we're starting chapter 10. Okay. Okay, so molecular geometry. One of the things that you can do with a Lewis structure is analyze it, that's what we're going to talk about now, to figure out what three-dimensional shape the molecule will actually have. Okay? So the theory that's used has the acronym VSEPR. It's often pronounced VSEPR theory. That stands for valence shell electron pair repulsion theory. The heart of this theory is this right here. repulsion. Electrons, as you know, are negatively charged, right? So they will tend to repel each other if they can, and that affects the three-dimensional shape of molecules. Okay. So it's going to allow us to predict the three-dimensional shape of molecules. We are going to start with two examples, actually. Did you guys did exceptions to the octet rule? No. Oh. A sort of vague yes. Maybe? Okay. Exceptions to the octet rule. This is an exception to the octet rule. There's two categories of exceptions to the octet rule. Small atoms can sometimes be in a dot structure with fewer than 8 electrons. So small atoms sometimes have fewer than 8 electrons. So beryllium chloride looks like this. Now, you do have periodic table. So beryllium is up there, number 4. So it has 2 valence electrons. Chlorine, each chlorine has 7. Okay? So 1, 2, 3, 4, 5, 6, 7 from one chlorine, 1, 2 from a beryllium, 1, 2, 3, 4, 5, 6, 7. If you add it all up, this is all the electrons that you have, right? You have 14 plus 2 is 16. That's it. So that's the structure of BeCl2, because Be is a small atom. It works out, exception to the octet rule. Okay, carbon dioxide we just did. Okay, what these have in common is, first of all, they both have 3 atoms. But they also both have a bond with an atom on the right and a bond with an atom on the left. The only difference is this is a single bond, and these are double bonds. Okay? So in this theory, VSEPR theory, you always focus on the central atom. So the central atom has 2 electron groups. I'm purposely using a vague word there. I didn't say bonds. I didn't say pairs. I said groups. Sometimes they are called electron sets. Let me just see. Total number of electron pairs. Yeah, I don't like the way your book says it. I'm just going to call them electron groups. Okay? So I said 2 electron groups. This has 1 group over here and 1 group over there. Carbon dioxide has the same situation. I don't care that it's a double bond instead of a single bond, because they're stuck. These 2 are stuck in the same place. They're between the C and the O. Okay? So an electron group may be a single bond, a double bond, a triple bond, or a lone pair. Any one of those things, I'm just going to call an electron group for the purposes of this theory. Okay, so if I have 2 electron groups and you know that electrons repel each other. So here's my two oxygens here. Let's say I'm the carbon. What's the best situation to keep these electrons as far apart from each other as possible? To be in a straight line, right? If I bring them any closer in any direction, that's not the best case scenario. The best thing is to put them 180 degrees, exactly opposite of each other. So what this valence shell or electron pair repulsion theory says is if there's two electron groups, they will repel each other get as far away from each other as possible, and that makes a 180-degree angle. So whether you're talking about the BeCl2 or the carbon dioxide, both of them you would predict to have 180 degrees right here. It's 180 degrees. 180 degrees. Now, the name of this shape is linear. So this is a model of carbon dioxide. Carbon's black, oxygen's red. So you see that it is a straight line. It doesn't matter what the double bonds are, where they look like. We're just looking at the O to the C to the O. That's a straight line. Okay. How do you tell the number of electron groups? You always focus on the central atom. So I don't really care about chlorine. I'm just looking at beryllium. And I'm just looking at what's around beryllium. So it was one single bond and another single bond. So that's 2 electron groups.
For the oxygen, there would be 4?
You're never going to look at oxygen because oxygen is not the central atom.
I mean, well, for that scenario, it would be 4 electron groups?
For carbon?
Yeah.
No. This carbon has 2 electron groups. Electron groups can be, a single bond counts as 1 electron group. A double bond counts as 1 electron group. A triple bond counts as 1 electron group. And a non-bonding pair or lone pair counts as 1 electron group. So that's why I use the word group instead of pairs, because a group could be 2 or 4 or 6. Okay? The reason that these two do not count separately is because, as this model is showing, these electrons and these electrons are there to bind C to O. This can't go somewhere else or the molecule falls apart. Whereas these electrons can and will, these electrons will repel these electrons. They have no choice about repelling each other, they're just stuck together. But these can repel these and cause it to be linear instead of a bent molecule. Okay. So now, we're going to build up to more and more complicated molecules just by adding more atoms / electron groups. So the next one we're going to look at is boron trifluoride, BF3. Okay. This is another example that is actually often done with an exception to the octet rule where boron just has 6 electrons. So now, the number of electron groups on boron. So boron, how many electron groups are around that B? 3. It happens to be 3 single bonds. So 3 electron groups, if you have 3 atoms bonded and they're all trying to repel each other. Well, picture the straight line. If you had a straight line and then 2 more electrons came in, what's going to happen to these electrons? They're going to run away. They're going to get repelled down this way. And so you wind up with Mercedes-Benz. There's the boron, there's the fluorines. It's perfectly symmetrical because these electrons repel these ones just as much as they repel these ones, right? They're all going to repel equally. So it ends up perfectly symmetrical. Unfortunately, I don't have, well, actually, I can do an example in a second. So this is the shape of it. Now, from the wonderful world of geometry, does anybody know what's the angle here? If you take a circle and chop it in 3, it's 120. 120 degrees from here to here, from here to here, from here to here. Okay? So, when I'm drawing a dot structure to analyze it, I'm not supposed to know the answer yet. So I didn't draw this with the nice triangle shape. It doesn't matter. This was just my dot structure. This shape now is called trigonal planar, which really just means flat triangle. Planar is flat, trigonal triangle, so trigonal planar. I can give you another example. Of a molecule that fits in this category, formaldehyde. I'm just giving you the dot structure. You can convince yourself later if you want to that this works, octet rule, valence electrons, all that. So the central atom is what in that molecule? Carbon. So how many electron groups are around carbon? 3. Remember, single bond counts as 1, single bond counts as another, double bond, so it's still 3 electron groups. So this one would also be trigonal planar. Okay, so that would just look like this. So hydrogens are yellow in this kit here. So even though the bond looks different just because you have to use springs to make it work, you see how it has that triangular shape, right? From the carbon's perspective, it's triangular. Okay? So I'm going to do all the examples that have no lone pairs first. Maybe. What about this? Actually, I changed my mind. I'm going to do this one next. Okay, sulfur dioxide. Okay, what's the total number of valence electrons for one s and 2 O's? Should be 18. S and O are in the same family, so they all have 6 valence electrons times 3 is 18. I'm not going to go through the whole thing, but 2, 4, 6, 8, 10, 12, 14, 16, 18. Just, you know, that is the dot structure. Now, the central atom is S. How many electron groups are there on S? This is still 3 electron groups. You have a single bond, a double bond, and a lone pair. That counts as 3. So single, double, and lone pair. Those are the 3 types. Okay, now what that means is the electrons are still going to repel each other just the way they did in BF3, boron trifluoride. If you have 3 electron pairs, it's still going to form the electron geometry is trigonal planar. But the molecule is actually not trigonal planar because even though this isn't S's, if I took the atom off of here, it's not part of the molecule anymore. So, and you can't see these electrons. You can't see the lone pair. It doesn't look like a triangle anymore, really. It's not the same type, right? A triangle. So, even though the electron geometry still has that trigonal planar shape, the molecular geometry is something different. So, when you have lone pairs, the molecular geometry actually has a different name from the electron geometry. The other examples we did, there was no lone pairs, so the electron geometry and the molecular geometry are the same thing. So, the molecular geometry in this case, after the fancy trigonal planar terminology, this is just called bent, right? SO2 is a bent molecule. Okay. So, now, lone pairs actually take up more space than a bond, meaning if I have 2 electrons here, they're not confined the same way these 2 electrons are really confined. They're stuck in this bond. These 4 electrons are stuck in this bond, but these guys, they can really spread out. So what happens is these get squished together a tiny bit. So your SO2 would look something like this. It just gets a little bit squished so that you have slightly less than, you would have less than 120 degrees. 120 is the perfect when all 3 sides are the exact same thing. If you have a lone pair on top, the angle underneath becomes a little bit smaller. Okay, so first we did 2 electron groups. Then we did 3 electron groups, and there's 2 possibilities, without lone pairs and with lone pairs. So now we're going to go to CH4 methane, CH4. So the number of electron groups here on the carbon, how many electron groups? 4 electron groups. Now this one is a little harder to visualize. But if you start with that triangle, if you start with a shape like this, and you bring some electrons in from the side. So imagine you have this flat thing right here, and here comes 2 more electrons. What's going to happen to these guys? They're going to fold back kind of like an umbrella. When it's really windy, the umbrella goes the other way. Okay, so it winds up looking like this. They can't be flat in the plane anymore because this one came in and bent them back. So this shape is called a tetrahedron. Okay? This is actually the optimal shape for these four sticks getting as far apart from each other as possible. And they're equal. It's totally symmetric. So the shape is called tetrahedral shape. The noun would be, it is a tetrahedron. The angle is 109.5 degrees C. That's what you would get if you think of a three-dimensional sphere and cut up the angles. Okay, now this example, CH4, has no lone pairs. So that means tetrahedral, that's the shape that the electrons are in, that's the shape that the molecule is. It's the same thing. You're taking a second? I'm just going to finish up the tetrahedral stuff. So probably 10 more minutes or so. Okay, so next one, NH3. You probably did NH3 as a dot structure. Okay, so central atom is nitrogen. How many electron groups? It's still 4. 4 electron groups. So that means the electron geometry is still tetrahedral. But in this case, the 4 electron groups are actually 1 lone pair plus 3 bonds to atoms. So what happens is the electrons are still like a tetrahedron, but if you take the top off, it doesn't look like a tetrahedron anymore. So what this one is called is trigonal pyramid, or trigonal pyramidal if you want to make it an adjective. So it's like a pyramid, except unlike the ones in Egypt, it has a triangle on the bottom instead of a square. So trigonal pyramid. Okay? So you notice this is not the same thing as trigonal planar. Trigonal planar is flat, and you would, if it was on my hand, all 4 atoms would be touching my hand. But this one is actually standing up a little bit, right? So that's trigonal pyramids raised. So this one, anytime you have lone pairs, that's going to affect the angles. Lone pairs hog a lot of space. They squish the angles together. So this angle is a little less than the regular. Okay, 109.5 is when everything is an atom, 4 atoms are attached. If you have a lone pair, then it's less than 109.5. Okay, last one for now. H2O. Who can tell me what H2O's dot structure looks like? Oh, you're jumping ahead. Okay, you have H. So that's the dot structure for water, right? You have to have the lone pairs on there to use up oxygen's valence electrons, but also so that oxygen gets the octet. Okay, so electron groups on O. Again, it's 4 electron groups. Where am I getting 4 from? Well, there's 2 sets of lone pairs, And then there's 2, in this case, single bonds. Okay, so 4 electron groups means the electron geometry is still tetrahedral. But if we go back to our tetrahedron, that's how the electrons are arranged, but 2 atoms are missing. So what's left is a bent shape. So when you have 4 electron groups, but 2 of them are lone pairs, and only 2 of them actually lead to atoms, the molecular geometry is bent. So, so far, basically went through your 2 electron groups, the 3 electron groups, and the 4 electron groups around the central atom and the possibilities for whether there's lone pairs or not. So what you're going to do is when you do a dot structure, first count up how many electron groups. Then decide, are any of them lone pairs? And from there, you can sort out, is it tetrahedral, trigonal planar, trigonal pyramidal, bent, etc. There are going to be some other ones that you'll get to probably next time. Okay? So why don't we take a little break, and Valentina is actually going to do practice problems with you guys on this same topic. Okay?